All right. Now, let's talk a little bit about p-values. P-values, you've probably heard about them. You've probably heard there's controversies and so on. I don't want you to think about them that way. They're just going to be statistics. They're just going to be things that you can observe from data, and they're used to characterize some aspect of a probability distribution. There's nothing wrong with them. There's nothing controversial per se. They're just a statistic. They're a nice statistic. They allow us to kind of solve many problems all at once. All right. That said, if you use p-values in a dumb way, naively, they can give you bad answers and ridiculous answers, in fact. And that's where the controversy arises. Usage of p-values. It's not p-values per se. It's like, is a car a bad thing? Well, no, cars are not bad things, but can you use a car badly? You know, by driving it too fast? Yeah. Okay. So similarly here. Okay, so this slide may take a little thought on your part if you haven't seen it before. Okay. I'm introducing it here in the context of Neyman Pearson, but I'm going to be using it in other contexts as well. All right, so consider a simple null hypothesis P. Okay, that bolded kind of P there just means I need to have a different kind of P down later, so I'm interested in this special P here. There's nothing particularly special about it. It's just a probability distribution that it represents the data that you get when the null hypothesis is true. Okay, now you get some data, let's call that X. And now let's consider a statistic T of X, just means some function of the data. And this could be the thing that your decision, it's just some function of the data. All right, let's suppose this T of X has a continuous distribution of the null, okay? And now let F of T denote its so-called tail CDF. What's a tail CDF? It's just the probability that capital T is bigger than little t. So this is the right-hand tail of the probability. It was that blue shaded region called FP on the previous slide. Okay, it's just the probability under the null hypothesis that your statistic that you got after you got the X is bigger than some threshold little t. That's what F of T is, okay? The tail cumulative distribution function, tail CDF. All right, now we define the p-value as, it's just going to be a random variable. P is equal to that F function. F is just a function, F of little t up there, right? Because once I tell you little t, then the probability that capital T is bigger than little t is just a number. It could be 0.3 or 0.2. It's just some number for each little t. Okay. But now what I'm doing is I'm plugging into this F function the random variable t. Okay. And so F of a random variable is a random variable, and so P, the P value, is a random variable. Okay. So the null hypothesis is true. I got some data X. I put that into my, little function, capital T. I got a number of some kind, all right? Then I put it into its own tail CDF, all right? And I transform capital T into some other number, all right? Which is a probability number now, tail probability. And I called that number P. So P is a random variable, okay? Became a function of the data. So P has a distribution itself, all right, under this null hypothesis script P. All right, so this is a little calculation that I want you to do all by yourself. I want you to see if you can take out a blank sheet of paper after lecture and do this all by yourself. Okay, if you get stuck, which I kind of hope you will, because that'll be a good opportunity for a learning experience, then try it again. Okay, so script P, the probability that the P value is less than some little p number is equal to, well, the P value by definition is F of T, so I plug that in. All right, now this tail CDF, because we have a continuous distribution, is invertible, okay, it's monotone. So I can invert inside of the event is not changed by applying F inverse to both sides of my little inequality inside of that probability. The event does not change. So I can play F inverse to both sides. So on the left-hand side, I'll get capital T less than now F inverse of P on the right-hand side. Okay, that's just, I can apply a monotone transformation to both, to both sides of inequality and not change the event. All right, and now the probability that capital T is bigger than, now think of F inverse as little p as just a, a Z or whatever. It's just another threshold number. It's just a number, okay? So go back up to the definition, that just gives you F of that number, F of F inverse of P. All right, and then F of F inverse goes away and I just get a little p. So this says the probability distribution under the null of the p-value is the uniform distribution. okay? Because if the probability of being less than some little p is equal to p, that means you have a uniform distribution. Okay, so that means we can do a lot of work just with the uniform distribution. We can do all kinds of calculations, and it's as if we're working with arbitrary distributions, continuous distributions, because we could have taken the continuous distribution, done this p-value transform, worked with the p-value, and then gone backwards, all right? So we don't have to work with a different distribution and work with all possible distributions and treat them separately. We can treat a whole bunch of them all together by just working with p-values, because they have a fixed distribution, a uniform distribution under the null, no matter what distribution you have. Script p here is a distribution. I call that a simple null hypothesis, but let's just be clear what that really means. It means there's a probability distribution in the case where the null hypothesis is true. Okay, so it's that Gaussian on the left, if you will. Okay, that red Gaussian. So that's the script p. It's a probability distribution. Okay, now the other p here is the p-value. Okay, it's a capital P. It's not a distribution. Okay, it is a random variable. All right, if you'll remember from your your probability 140 or whatever, a random variable is a function from the sample space to the real line. So it's a real valued thing that takes on different values as you draw. Okay, and that's in fact exactly what's happening here. P, the Roman P, is just a number. How do you get that number? Right? Well, in a kind of a complicated way. What you do is you define this tail probability under the p distribution. Okay, so p is the only distribution in this old slide. It's the only probability distribution. So under the p distribution, t of x, which is just some function applied to the data x. So x is being drawn from this p. And then you apply t to it, like, it's a little Python function. You take in, you look at x, that's your data, and you maybe take a median or something. You take some function of your x. Median wouldn't be good. That's not continuous. But anyway, maybe you square it or, add 5 to it or whatever. That's what t does. It just is a function. Okay. And now we say, what's the probability that t is bigger than little t? That's a tail probability. It's probably that you're to the right of the cutoff little t. So that probability that t is greater than t, that's just a number. Under the probability distribution script p, it's a number. It's like 0.1 or 0.5 or whatever. It's probably that you're to the right of some little t. Okay. In that diagram I had, a couple slides ago, it's the area on the curve to the right of the threshold. All right. So that's what f of t, f of little t is. So f of little t is just a number. I tell you a threshold value like 45, and you tell me what's the probability to the right of that. That's f of t, maybe 0.05. All right. So that's what f of little t is. All right, now if I take my statistic t of x, which is a random variable, and I plop that into the argument of f, that's f of capital T, okay? Now I'm getting a random variable, and I call that p, okay? It's this function evaluated at a random variable t. Okay, so that's what the p-value is. It's just the tail probability of the statistic t of x. Okay. And then the last thing at the bottom is really just this calculation. It just says, okay, you want to calculate the probability that this new random variable that you defined called the p-value is less than p. That is the cumulative distribution function of the p-value, right? It's a probability that this random variable is p is less than some little p. That's a cumulative distribution function. Okay, so the probability of that is just by definition p of, then you plug in the f of t. Okay, and so now this f of t, remember, is a tail CDF. If you go back up to the definition up there, right? It's the probability that capital T is bigger than little t. Think what happens as little t gets larger and larger and larger. It goes from 5 to 10 to 20 and so on. The probability that big T is bigger than that is going down, right? Because the probability of being to the right of some threshold goes down as the threshold gets larger. Okay, so f of t is a monotone decreasing function, f of t. And if I had my little slate right now, I'd draw that, sloping down function. All right, so now the probability that f of t is less than p, down at the very bottom. All right, if I apply f inverse to both sides, f was monotone decreasing. So when I apply f inverse, I switch the inequality. And that one I really want you to try to do yourself. Okay, think about that for a second. Draw this out. That would be a step where, you don't even need much probability to do this. Just draw out this and try to see if you can get that. Okay. And then if you've gotten that, then we just plug back into the definition. P, the T is greater than or equal to F inverse of P. Well, that's just this, by definition, F of F inverse of P. I'll plug that in and then I get P. Okay, so I talked that through a little bit slowly, but hopefully that was helpful. It's also now recorded, so that can help you. But I really would try to see if you can go through each one of the little steps here. We're not doing a huge amount of probability here, but these kind of basic definitions, and then what's called the tower property, kind of the expectation of expectations kind of things. That's kind of the probability theory that we're going to be using in this class mostly. All right, so I hopefully can now keep going. Okay, there we go. Okay, so given that we've had that sort of new definition of a p-value, we're going to have kind of, we talk about a generic decision rule, that we're going to reject a null hypothesis if some random variable that we choose in some way, t sub I, is equal to 1. And t sub I is being chosen in a very special way. It's a threshold. We choose it to be equal to 1 if the p-value is small and 0 otherwise. Okay, so this p-value is a tail probability. If that's small, that means you're to the right of a threshold. So this says if you're to the right of some threshold, determined in this interesting way, okay, then we reject. We make our decision equal to 1. Otherwise, we accept. We make our decision equal to 0. So this accommodates that particular case that we had of Gaussian distributions on the previous slide, where we had a p-value given by that little kind of area under the Gaussian curve, all right? And we rejected if we were out on the beyond that threshold. Otherwise, we accepted, all right? But what I've the p-value idea is more general than those Gaussians, okay? And it's just a probability of under any distribution, not necessarily a Gaussian. All right, now I've made this even more general than I needed to for that little example. Here, I'm allowing myself not just to have each one of the HIs in a sequence of them can be different, and the alpha i's can be different for all the different tests. So I'm going towards where I'm heading here. I'm going to have a whole bag of tests, and they can be different tests. They don't have to be the same one over and over again. Right? But if you do the same one over and over again, and you all set all the alphas equal to 0.05, that's the Neyman Pearson setting that we've been talking about. Okay, I want to move on now to multiple hypotheses, where I've been aiming for. Okay, so now let's really consider the case of multiple tests. We're trying to do like mini coronavirus tests or mini fraudulent tests or whatever, or just maybe tests in some scientific field of some kind, and they don't even have to be the same test. And I just want to make sure that over the whole bag of tests that I'm doing pretty well. And that kind of relates to that false discovery idea before. That was kind of like, of the bag of discoveries you made, can you guarantee me that most of those are not false discoveries? Okay, that's the kind of thing I'd like to aim for. But in general, it doesn't have to be false discoveries. If we just over a bag of tests, can you guarantee me that most of the answers you're giving are pretty good? All right, now the row-focused Neyman Pearson paradigm doesn't really help you so much with that. It only focuses on cases where the null hypothesis is true. What about the cases where it's not true? And what about the cases that you're getting some cases that are true and some are not, and you don't know which is which? It's just not so natural there. All right, in particular, when the cases are arising from some underlying prevalence, you're going out and doing coronavirus testing, for example, you're walking down the street, you know, you might get a person who is a case and another person who's not, i.e. the null hypothesis is true or not. And they're blended in some way given according to the actual prevalence. And you'd like to be taking that into account in your testing paradigm. Neyman Pearson doesn't do that. All right. Also, when we're talking about a bag of different tests, maybe we're testing for the flu and SARS, 1 and so on. We might have a whole bag of tests, and we want to make sure we're doing well over the entire set. So I said CF/AB testing. That's the kind of industry term for doing a large set of tests. Like on my website, should I put blue color or green color, or should I have a different kind of widget? How do I set up respond to customers kind of website or something? That's called A/B testing. Okay, so here's a little favorite cartoon that's going to set this problem up. All right, so we're now going to have multiple decisions. What is the kind of core statistical problem here when we're not talking about kind of one hypothesis test? We're really now trying to focus on this multiple tests. We want to have a priori control over some kind of error over the whole set of tests. All right, so here's a real life problem. Someone comes running in the room. They say, oh, I have a hypothesis. My hypothesis is that jelly beans cause acne. Okay, you all know what a jelly bean is, hopefully, and you know that acne is a skin condition. And the person in the room says, oh, scientists, come investigate. The scientists are over in the next room. They're saying, but we're playing Minecraft. And, okay, fine. Then they go off and do some kind of statistical test, i.e. they gather a bunch of data. They gather the right number of people. They randomize. Maybe take 50 people, 100 people, and at random take 50 of them and give them jelly beans for a month. And 50 people are the control. They got no jelly beans. And then after the month has gone by, they look at the number of people in the control who have bad skin and look at the people in the got the jelly beans that have bad skin, measure the skin in some way, and calculate a statistic, T of X, based on all the data they saw. And then they, from that T of X, calculate a p-value. And they did that here. They are good statisticians or good data scientists. And they found that there's a p-value is bigger than 0.05, okay? Meaning that they're not past that threshold, that cutoff. Therefore, they accept the null hypothesis, meaning there's no link between jelly beans and acne. Things look like they've worked out pretty well here. Of course, probably there is no link between jelly beans and acne. That seems like a dumb hypothesis. And just to say, in many areas of science and in technology, people have dumb hypotheses all the time. They should, right? Because they're trying to explore. In mature fields, people have explored all of the easy hypotheses first. That's been done in the past. The ones remaining to discover are probably pretty weird and pretty strange. And most of them are going to be false, the ones you think about. So you've got to really have a good test. Okay, so in the classical textbook, you'd be done now because you've settled the problem. You've made a good decision and everything is happy. But in real life, people are never satisfied with that. They say, well, wait a minute, I hear it's only a certain color that causes it. And this is typical in business, right? If you're in a hedge fund and you come in and say, I got some great new idea that, you know, if it gets cold in Japan, that means the price of fish goes down or something like that. And therefore, I'm going to bet on a certain stock because it's now cold in Japan. And then you test that on actual data in the past. You say, oh, that didn't work out. That's not true. So you don't, invest and you don't lose your money. Right. But then then what do you do with your money? You just can't sit there. You got to invest it somehow. So someone says, well, no, it's not only when it's cold. It's when it's cold and we're in December, whatever. And people have all these great little stupid ideas and you have to keep trying them. So what you're going to do is you're going to bring the scientists back in the room and they're going to now do a test on all the little hypotheses that now many people have or one person has. So in this little picture here, they've tested now purple jelly beans and salmon jelly beans and red jelly beans and turquoise and blah, blah, blah. And in all these cases, the scientists did a great job. They got 100 new fresh people, put 50 of them, randomly in the jelly beans and 50, no jelly beans, waited for a month, so on and so forth. And we know what's going to happen, right? By chance alone, at some point, you took the 50 people you randomly assigned to the jelly beans condition already happened to have bad skin. And the 50 people you assigned to the no jelly beans didn't have bad skin. You waited for a month, you looked at them, and you say, oh my God, there's bad skin in the jelly beans condition. And then you quantify that, you calculate your p-value, and you see it's p less than 0.05. That means you have a result, okay? But you don't really have a result. This is an error. This is a false discovery, probably, right? But it's going to happen because by chance alone, you're going to have this thing happening, all right? And the problem is that as soon as you make that discovery, you're going to throw away all the other no discoveries you made. No one's interested in those. But this one you can publish. The journal will take it because it's an actual new discovery. And moreover, because it's kind of so weird that green jelly beans cause acne, that seems unbelievable. Well, it's unbelievable because it's false. But it seems unbelievable and it's in a journal, so the newspapers are going to pick up on it and report it. This happens all the time. I hope you appreciate this as young data scientists, that this is a very, very common and serious problem. That people are doing lots of tests, they're not controlling for error rates. It's very highly probable they'll come up with a strange result. That result will look interesting, so it'll get amplified. So we have these kind of noise amplification processes in our society. How do we fix this? Well, we train people like you. You know how to fix it. Okay, so let's go through real quickly the classical attempt to fix this. It's called Bonferroni, and then we're going to move on to false discovery rates, which is the modern way to fix this. That's much more satisfying. Okay, so Bonferroni, this is still in the row-wise kind of approach to this. This is not going to be Bayesian. All right, it's pretty simple though, and it's not such a bad starting place. So let's suppose we're not just doing one test, now we're doing little m tests. Let's define a new random variable, okay, v. V will be the number of false positive errors in our m tests. Okay, just a count of our m tests. Maybe m is 100. We're doing 100 tests. Maybe 30 of them are false positive errors. Now we don't know how many are false positive errors. We're not the supreme being, right? But we can define this random variable v. Moreover, let the event ei equals 1 denote the event of a false positive error on the ith tests. Right? Again, we don't know this, but as mathematicians, we can define this. All right, so now we're going to do a whole bunch of tests. And instead, on each one of these tests of using a rejection threshold of alpha, if your p-value is less than alpha, you reject. For each one of our tests, we're going to use alpha divided by m. So if alpha was 0.05 and we have 100 tests, this is 0.05 divided by 100. So it's 0.0005. Okay, so we're going to have much more stringent. You have to be really far out there in the tail to make a rejection now. So we're not going to make many rejections. All right. So are we controlling a certain error rate now? This seems like an okay, reasonable thing to do, but are we controlling some error rate? And here's another little piece of mathematics that, again, I kind of want you to go through. It's elementary. All right. But if this is not familiar, it's a good kind of stopping place for you to sort of say, I need to understand this. Okay. So now I'm using, unfortunately, I'm using p now as the probability. I should have used that script p here on this slide, because this is not the p-value. This is a regular, good old-fashioned probability p. But I'm going to be using p in this way in the future. I just used it on that slide because I had the two p's, and I usually don't have two p's. All right. Anyway, the probability that v is greater or equal to 1. What is that? That's a probability that you made one or more false positives. The count is bigger than 1. What is that? Well, that's the probability of the union of these events. Okay, to make one or more false positives, you had to make a false positive on one of those tests. EI had to be 1 on one of those or more. Okay, so this is the probability of 1 or more, which is the union of all those events that you made an error. All right, now there's a very important result. This is called the union bound, or somehow the Boole inequality. Again, back to data 140. The probability of a union is less than or equal to the sum of the probabilities. Okay, draw yourself a Venn diagram, but hopefully you know this. So I pull that probability inside and I have the sum outside. All right, now what's the probability that EI is equal to 1? Well, that's the probability of a false positive. All right, and I'm controlling that under this Neyman Pearson style thinking at no more than my threshold value, which is alpha over m. So I have a sum I equal 1 to m of alpha over m, and now you can do the arithmetic that shows you that that's alpha. So by using alpha over m instead of alpha, we're making sure that the probability of making one or more false positives is less than or equal to alpha. So if alpha is 0.05, I can guarantee you that even if you only did 100 tests, the probability you're making one or more false positives is really controlled. So in our jelly beans case, if instead of using alpha equals 0.05 on each one of those jelly beans tests, if you use 0.0005, then over the entire set of 100 tests you can do, I can guarantee the probability you made any errors is still small. Now, if people were to do this on these jelly bean situations, life would be better in the world. We would have fewer of these ridiculous false positives that are cluttering our lives, right? This is controlling the family-wise error rate, the FWER. All right, so here's a picture, and I'm probably going to be ending with these pictures here. I got 4 more minutes on my clock. So here, these are p-values from 25 different experiments. So p-values, right, are small. That means you should be rejecting. Those are the small ones here. The big p-values here are big. Those means you should not be rejecting. You're on the left side of the diagram. All right, so we have to set a threshold. So let's suppose we just do the naive thing and put 0.05 as our threshold, like right there. Naive multiple decision making. And everything below the threshold, we reject. If we had one hypothesis, it would be Neyman Pearson. It would be great. But we don't have one hypothesis, right? We have a whole bunch of them. And so suppose the oracle or the supreme being knows that in fact those red cases were actually cases you should reject, but the blue ones were not. Okay, the red ones were actually cases where the null is false. All right, so if we put our threshold back up there again, you can see that we rejected 11 times, all right? And 7 of them are red. That's good. We should have rejected, but 4 of them are blue, if you count. 4 of those little bars are blue. They're under the threshold. So those were errors. So 4 of my 11 discoveries were actually false. My false discovery proportion is 4 over 11. And again, I would argue that's pretty bad. So we're not doing anything like 5% error rate here. We're doing something worse according to that particular measure. What is about Bonferroni? Well, Bonferroni divides that threshold by the total number of tests, which is 25 here. So the overall threshold will go way down to be 0.05 divided by 25. All right, so now we're not making any rejections hardly at all, but we made 2. But unfortunately, one of our 2 rejections was a false discovery. And so our false discovery portion now is actually even worse. It's 1/2. Of my discoveries, half of them are false. So Bonferroni actually did not help me that much in this particular way of measuring things. Okay, how do you get out of this conundrum? And again, a classical class would have stopped here. They just would have said, that's life, folks. But we're going to do something different. And here's the big question. Is there something else we can do? And the real answer is going to be, we're going to be going to a Bayesian perspective. We're going to be looking at columns instead of rows. And that looking at columns is going to give us something else. We're going to be out of the box at this point. Instead of looking at thresholds that are flat, we're going to look at thresholds that are growing lines. Okay. Moreover, instead of working with p-values in the arbitrary order they came in, we're going to sort the p-values, at least in our first round of these ideas. So we sort the p-values from small to big, and then we're going to compare those p-values to a tilted line. And everything that's below that tilted line, we're going to reject. And everything above that tilted line, we're going to accept. This is called the Benyamini-Hochberg procedure. And this is really pretty cool. This is really what should be done in lots and lots of fields of science. And more it is being done, but it is taking time. Okay, so the basic idea is kind of interesting. It's, you will probably not see this plot in any classical statistics book and not even very many modern ones, but the basic idea is going to be, we're not going to use a flat threshold anymore of a p-value. What we're going to do is have this little line here, in some sense, as our threshold. What we're going to do is take all of our p-values, and we're going to sort them from smallest to largest, okay? All right, now, if we had no signals here whatsoever, everything is null, there's no discoveries to make whatsoever, we again expect a uniform distribution. So even after we sorted them, we should see that uniformity, and what we'd be getting is just a 45-degree line of these hypotheses stepping up. All right, the fact that there's kind of a bend in the curve a little bit here, there's a bunch of them that are really pretty small, that are kind of below the 45 degrees, and then eventually they come up above, or they start to approach the 45-degree line. That suggests that there's a few signals that are so small that, they're not expected by chance. All right, so what we're going to be doing is sorting the hypotheses, and then we're going to draw a particular line there. It's not the 45-degree line, in fact. It's a particular line. And what we're going to do is we're going to walk along until we get the last hypothesis, which is below the line. All right, I'll be making this clear in a moment, but just to tell you that that's what we're going to do. We're going to walk along from left to right, and we're going to look at a hypothesis. Is it below the line? Is it below the line? That's fine. And then maybe it goes back above the line, but I keep walking along until I find one more that maybe is below the line. And then when I get the last one that's below the line, I stop there, and I reject everything to the left of me. Okay, this is called the Benyamini-Hochberg procedure. Okay, it sorts the p-values, all right? Then it draws a particular line that I'll tell you about in a second. Right? Then it walks from left to right, and it finds the last hypothesis, which is below that line. Once it's found that one, it rejects that hypothesis and everything to the left of that. All right, so all those really small p-values we're rejecting. That's good. All right, and we might be rejecting a few of the null hypotheses, but the null hypotheses, are uniformly distributed, so maybe not too many of them over there on the left. That's kind of going to be roughly the idea. Okay, so to kind of give you a flavor of where this is coming from, so what I intend to do is I'm going to write down this little Benyamini-Hochberg algorithm. It's something you can put on the computer really easily. It's something you can do for the rest of your career. It's a good thing to do. I'm going to give you a little argument that suggests where it's coming from, and we're not going to get all the way to a proof because the proof is actually a little more complicated. It involves martingales, and that's kind of coming about because of this sorting is happening, and it kind of gets a little complex. Instead, what I'm going to do is move on to what I think is even a more interesting problem that sounds more complicated. It's the online false discovery rate problem. But actually, it's less complicated in a certain sense, and I'm going to actually be able to give you a full rigorous proof there. Okay, so that's going to be the goal of the lecture. Hopefully, we'll get all the way through all of that. All right, so let's remember this little Bayesian calculation we did. You always have to kind of be willing to, or ready and willing to break out Bayes' theorem in lots of statistical problems. Okay, all right, if we're thinking about false discovery things or kind of, you know, anything that's column-wise, what we're going to do is write down a conditional probability like on the left of this page here. We're going to say something like, the probability given that D is equal to 1, that puts me in the rightmost column. So I'm obviously talking about a column-wise kind of quantity. And then I'm asking, what's the probability that H is equal to 0 given that you're in the first column? If you're in the first column, you made a decision that you made a discovery. And what's the probability that H is equal to 0 there? I.e., what's the probability that you made an error? Okay. So what do you do with that? Well, you might think about Bayes' theorem. So let's just go ahead and do that. I reverse the conditional, and I get probability D equals 1 given H equal to 0. Okay. And then probability H equals 0 divided by probability D equals 1, just Bayes' theorem. All right, that first term in the numerator there is a likelihood. Okay, a likelihood is not the probability of H given D, it's the probability of D given H. Right? The way the language is being used here is that it's the likelihood of seeing that data that led to D equals 1, given that H is equal to 0. So it kind of provides some evidence for H equals 0. If that's kind of a high probability, then you say, yeah, it looks like H equals 0 is a plausible explanation for it. But it's kind of backwards logic somehow. It sort of says, I'm not talking about the probability of H equals 0. I'm talking about, given that H is equal to 0, what data should I expect? And did I see that? It's kind of a little strange logic, but anyway, that's part of statistics. That's the likelihood. And then we multiply by the prior, which is probability H equals 0. Okay. In our disease kind of situation, for example, probability H is equal to 0 is probability that you don't have the disease. And for many, many diseases, as you're walking around in life, you hope you don't have the disease mostly. And so probability H equals 0 is a big number in most situations. Okay. Okay, so if that's a big number up there, by the way, that means on the left-hand side, all else being equal, you should have kind of a big number. In other words, if you make a discovery, someone says, oops, your test came back positive, you say, well, wait a minute, that looks like it's pretty likely to be a false positive, okay, because the prior was really low. Okay, so that's kind of the spiritually what a Bayes' theorem is giving you, is it takes your worry away a little bit. Okay, now in the second line of this slide, I kind of just put in some different language. So P of D is equal to 1 given H equals 0. Well, D being 1 when H is 0, that's a false positive. So I just called that the probability of a false positive, okay? It's the kind of quantity that Neyman Pearson we're working with. It's kind of it's a row-wise quantity, right? Because it's in the first row. Then we multiply by, and I put in some notation for P of H equals 0, just like last time. I called that pi naught. And then I left P equals D, P of D equals 1 alone. All right, now we'd like to control this quantity on the left. We'd like to control means keep it small. We'd like to have few of these errors, okay, that probability H equals 0 given D equals 1, few of these. So we'd like this whole thing to be less than or equal to something small. So how do we make this thing on the right less than or equal to something small? Well, we make the numerator small. We might even try to make the denominator big somehow, but let's try to make the numerator small. All right, how can we do that? All right, well, not so hard, really. Pi 0 is the probability that you have the disease. And like I alluded to earlier, we're often interested in situations where that probability is really, really low. Probability H equals 0 is probably you don't have a disease, right? So that probability is high, okay? Another way of saying this is the probability that with a situation where there's not many discoveries to make, okay? Mostly the null hypothesis is true, that some alternative you have in mind is just not, is too crazy. It doesn't really work out. And you keep trying alternatives, but you know, all the null is a pretty good hypothesis. It's hard to beat. Okay, so pretty often that pi naught is going to be a number close to 1. All right, so if we want to upper bound this right-hand side, we can just replace pi naught with a 1. And we are definitely doing an upper bound, and it's probably not a bad upper bound because pi naught is probably close to 1 in many problems we care about. If that's not true, then you want to rethink this logic, maybe not go down this path quite. Okay, so pi naught we can just erase. All right, what's the probability of a false positive? All right, well, that's the kind of thing that Neyman Pearson was talking about controlling, right? And so the machinery that was developed to do Neyman Pearson, like setting some threshold or something, can be borrowed here to try to keep that false positive rate small, like under 0.05 or something. Okay, so we really, you know, have to worry about the denominator. The numerator is not no real struggle here, but what about that denominator? Okay, in Bayesian work, this is often kind of a problem for Bayesians, which is they don't have any way to get hold of that denominator, control it. And you want, if you want to upper bound on the whole thing, you need a lower bound on the denominator. That's often kind of really hard to get. And so Bayesians often have to work hard and make lots of assumptions. All right, in particular, we can sort of see that. What is that denominator? Well, P of D equals 1. We can use the law of total probability. I alluded to this earlier. And write that out as the likelihood, P of D equals 1 given H equals 0, times the prior. And then plus the other likelihood, the probability D is equal to 1 given H equals 1. Okay, the likelihood under the hypothesis H equals 1 times its prior. All right, and then we can plug in our pi naught here. We see that we have pi naught times a likelihood plus 1 minus pi naught times the other likelihood. All right, so P of D is 1 depends on the prior. Okay, so if we were upper bounding pi naught with a 1 in the numerator, we can't do that in the denominator. We need a lower bound in the denominator to get an upper bound on the whole thing. So we're kind of stuck in the denominator. We can't plug in a natural bound of any kind for pi naught. Okay, so what are we going to do? And so again, you know, you're sort of, some problems you're sort of stuck, right? But here is a critical point, and this is, I want you to all wake up, you know, pay attention here. Here's a critical point, is that we're in this particular setting where we're not just looking at one hypothesis, H equals 0, and one decision, D equals 1. We're looking at a bag of them, a whole bunch of them, okay? And over this bag of hypotheses, where we're making many tests, on some fraction of them, we're going to say D equals 1, and on some fraction, we'll say D equals 0. So we'll make some discoveries, and we'll not make some discoveries. We can look at that fraction and sort of see how many times are we saying D equals to 1, right? In other words, we could estimate that P of D equals 1. That's a probability, you know, in the population, right? But after we've done a bunch of these tests, we can get a kind of a proportion estimate of that probability. We just count to the fraction, the proportion of the number of times we said D equals 1 over the total number of tests we did. So that means that denominator, when we have to try to expand it out and estimate all of its terms, that was the wrong path to go down. All we have to do is just stop with that P equals D equals 1 and say, is there a natural estimator from that, for that? And yeah, there is in this multiple testing situation. We just take the fraction of the number of times we made a discovery and we plug it in. Now, that is interesting. Or what happened is that we were kind of going down a Bayesian path, but then we just kind of plugged in an estimator, more like a frequentist kind of thing to do. Is that a weird thing to do? You know, no. Okay, this is actually a reasonable thing to do. Lots of statistics has this flavor. You start by making some probability statements using Bayes' theorem and all. You're being a Bayesian. And at some point, you kind of get a little stuck and you say, well, can I get an estimate of that quantity, just kind of in a frequentist sense? In other words, looking at repeated trials. And sometimes I can, I plug that in. This has a name. This is called empirical Bayesian, okay? We're taking a Bayesian posterior probability and we're plugging in a empirical estimate of some quantity, and that is called empirical Bayesian. I tend to really like empirical Bayesian thinking, so I really am glad that I wanted to introduce this to you folks in this class, and so I was eager enough to do that I thought I'd do it right on the first topic. Okay, so we're going to be doing that. We're going to be putting in an empirical estimate for P of D equals 1 and seeing what that gets us. All right, and in fact, that's going to get us this, these FDR controlling algorithms. Okay, so let's now talk about an FDR controlling algorithm that's kind of based on that style of thinking, that I kind of control the numerator in a simple way, and I plug in an estimator in the denominator. Okay, so the names associated with this are Benyamini Hochberg. This goes back already to 1995, where they wrote a paper proposing this algorithm that I've already mentioned. This interpretation that it has an empirical Bayes kind of perspective, they didn't have that. They were working from a purely frequentist point of view. And that perspective came out from some people, mainly at Stanford. There was John Story had a thesis on this, and Brad Efron has also argued this perspective. Okay, so here is the Benyamini-Hochberg algorithm. Again, I already mentioned it kind of briefly. I'm going to now be a little more formal. So given M tests, all right, so maybe 100 tests, M is equal to 100, say, all right? You do all these tests and you obtain p-values for each one of them, okay? So you have to do a little work there, you know, using your probability background or whatever to get these p-values. Sometimes you do a permutation test, which you may have learned, you remember learning back in data 8. There's various ways to get p-values. We'll be talking more about that as we go, but you know, thresholding something like a normal, that'll certainly give you a p-value, a tail probability, okay. Now, we obtain these p-values from our M test. Maybe we have now a bag of 100 p-values, all right? We're gonna sort them. We run a sorting algorithm, okay? We sort them from smallest to largest, like I did. And to note the sorted, there should be a P there. I erased that somehow. The sorted p-values as P with the parenthesis K parenthesis. Those are called the order statistics. That just means the sorted values of the PIs. That's what the parentheses mean, sorted values. Okay, now the small ones are the ones that are safest to reject, okay? Those are the ones that are probably not coming from the null, because the null is giving you uniform p-values between 0 and 1, and so it's not gonna give you a whole lot of small ones. So if they're small, it's maybe the case that they should be rejected, so go ahead and reject those. And you're gonna reject all the way up to some kind of a threshold. Again, it has a threshold rule, but it's in terms of this tilted line, really. And here is actually the algorithm written out, okay? So it's actually extremely simple. This is the whole algorithm, all right, after you do the sorting. Okay, what you do is you find the largest value of K, such that K divided by the total number of tests, M, which is maybe like 100 or something, times some alpha that you're trying to have as your overall control in the FDR. This isn't like the Neyman-Pearson alpha. It could be 0.05, but you have a different interpretation of it. You're trying to put the false discovery rate less than 0.05. So in my really bad example, those 10,000 A/B tests, my false discovery rate was like 495 over 575. You know, and that was the random version of it. But the false discovery rate is going to be the expected value of that proportion, and we want that expected proportion to be less than alpha. So we plug in an alpha, we choose it, maybe 0.1, maybe 0.05 or whatever. All right. M is fixed by the problem. And what we do then is we walk along and we find the biggest K such that the Kth p-value is less than or equal to that K over M times alpha. Now, K over M times alpha, that's a line, right? Because alpha is a fixed number, like 0.05. M is fixed number, you know, 100. Okay, so that's like a slope. And K is the index, it's the x-axis. Okay, so this is like K times the slope, which the slope is alpha over M. Okay. And we're plotted these p's of k's are just kind of, for each k, we have a number, you know, 0.03, 0.04, it grows, right, as we're walking along. All right, so we're kind of having a line that has a slope alpha over M, and we're looking at some values, and we're asking, are you staying below that line? And as long as you're staying below the line, you keep looking at bigger and bigger values of k. And eventually, you're going to arrive at a value of k that all the p-values after that are bigger than the line. They're greater than km over alpha, okay? And once you've arrived at that point, you're done. That's what the algorithm tells you to stop at. You stop there, and you reject everything to the left. You're rejecting the small p-values. All right, so hopefully that was clear. That is the Benyamini-Hochberg algorithm. It is a great algorithm to know, and we're going to try to now understand it a little bit better. There it is, and it's a picture. We took in this case, I think it was 25. M was 25. We sorted them from small to large. we drew our little line there, and now you know what that line is. Okay, that line is a line that has slope alpha over m. So m is 25. You know, think of alpha as like, you know, 0.05. So 0.05 divided by 25, that's the slope of that line. Okay. All right, and then k is just the index, and we walk along until we finally get all the p-values are above that line. And you can see that sort of happens. Again, I probably should make some better pictures here, but I think it happens about at p-value, you know, it looks like 11 or no, maybe 9 or something. After that, all the p-values are above. And you see that the ones to the left of that point mostly are red. In fact, the ones, the red ones we're missing, we're only missing 2 of the red ones. And the ones to the left, I think there's only 1 blue one. Okay, so we're getting, in fact, a good value of the FDP. We picked the right place to cut this thing off to make sure that among the things we rejected, most of them are good rejections. Okay, so you're going to reject null hypotheses, i.e. declare discoveries for all hypotheses such that you're below the that cutoff value, that red line there. Okay, actually that's not, I bet the red line is in the wrong place. I will fix that. All right, so this turns out to control the FDR. Now, what is the FDR? So I think I said it too quickly. I want to say it again. So FDP, that's the false discovery proportion. That's that that's that column-wise, you know, false positives divided by total number of discoveries. Okay, that number, the FDP, is a random variable because every time you get new data, you're going to get different counts, and you're going to get a different value of the FDP. Okay. We can't expect on any given experiment to have that ratio be less than 0.05 because by chance, you know, by some probability, it's going to just, we have bad luck. It's going to fluctuate, you know, up above. But as usual in statistics, we might hope that on average, over lots and lots of repeated trials, we can keep that FDP on average to be less than some value like 0.05. Right? What we're doing at this point is we're taking a frequentist perspective. And next time we're going to be talking more about what Bayesian means and what frequentist means. So they still might be a little mysterious. I hope to make them less mysterious next time. But just to say, when we talked about the expected value of the FDP, we had kind of gone down the road of writing down a Bayesian column-wise kind of thing. And then we eventually said, well, I want control over that in a frequentist sense. I want its expectation over lots and lots of trials of this, over lots of you know, attempts to do this procedure. Okay, so the expectation of the FDP, that is the FDR. All right, now you're going to see this math written out a little bit when we go to this other case of online, which I think is more simple. But for now, just let me sort of assert that this paper back in 1995 wrote down this algorithm, and it defined the FDR as the expectation of the FDP, and it proved that the FDR was less than or equal to alpha under this procedure, you know, under certain assumptions. Okay, so you're not seeing that proof here. I'm going to give you a little heuristic argument on the next page about that kind of proof. But it took then, you know, about 10 years after that for better proofs to come out. The first one was really quite complex. And the better proofs ended up using what are called martingales, which maybe you've learned about. You would learn about in grad school in any case. And so I'm not going to go through a martingale idea. So let's go back to this plot. And I don't really expect you to understand this. This is heuristic, first of all. It's just sitting there for you to kind of know this is sort of how you think about it. And if you really were to get into this literature and learn about it, this might help you understand the proofs and so on. But just again, this is the line we've been talking about here in the middle. That has slope alpha over m, as you can see here. All right. And what we're doing is that we're walking along until we arrive at point K. And if I were to plot all the p-values, they would have been below the line. And then after that, they would have come above the line. All right. Now I'm putting one more piece of information here. This gamma value, all right, is the value corresponding to K. All right. And if we do just a little bit of high school algebra, actually elementary school algebra, we can see that gamma is equal to what? Km, alpha K over m. Okay, there's a proportionality, right? Alpha over m is equal to gamma over K. I can solve that for gamma and I get alpha K over m. Okay? All right, so let me go down to this little heuristic argument here. And first of all, let's let m naught denote the true number of nulls, so the number of true nulls. So if I'm doing 1,000 tests, maybe 900 of them are true nulls, where I should not make a discovery. Those are people who don't have the coronavirus. Okay. and there's 100 people that do. So M naught is did I say 100? I've lost. So I'm doing 100 total tests. That's M, and let's say that M naught is 90. Let's suppose that's the number of true nulls. Okay, so 90 is kind of close to 100. Like I said before, most of the ones we're in this case we're interested in are null. All right, so here's my little argument that FDR is less than or equal to. Okay, now this first line here is interesting. The denominator is just K because that's the number of rejections I'm making. That's the number of discoveries. Okay, I just plugged that in because I was the one who determined how many discoveries I made by this algorithm. I went along until I made a cutoff, and then I rejected all K things to the left. So K is just given by the algorithm. Now on the top, again, I replaced the prior pi naught with a 1. And what this is the expected fraction of false positives. Okay, now why is that? Well, remember that under the null hypothesis, the fraction, the p-values have a uniform distribution. Okay, so the fraction of false positives are the cases where I'm below, in this case, gamma. Okay, that's the ones that are all these p-values over here are below gamma by definition of this algorithm. Okay, they're below gamma, and so gamma is a probability number, like 0.001 or something like that. And I multiply that by m naught, which is the total number of true nulls. Okay, and so I get the fraction of those true nulls, which I'm incorrectly rejecting because they're below this threshold value. So gamma times m naught is the expected fraction of false positives. And that's what I had on a slide a minute ago in one of those numerator quantities, the probability of a false positive. Okay, and then I just use my arithmetic to replace gamma with alpha k over m. That's just my little trivial arithmetic. All right, and now the k's cancel, and I get alpha m naught over m. And m naught is like 90 and m is like 100. So anyway, it's less than 1, and that's always going to be true. And so I get less than or equal to alpha. So this FDR, which is the expected number of false positives over the number of decisions roughly, it's the expected FDP, which is false positives over decisions, over discoveries, is less than or equal to alpha. Okay, so that's heuristic in a number of ways. And so I don't want you to sort of stare at this too long and say, oh my gosh, how do I interpret all this? What's really the probability? What's the proportion and all that? We're going to get to a real proof here a little bit later.
In this video, I want to examine the relationship between false discovery proportion and false discovery rates. These are two very related concepts, and the difference between them is a little bit subtle. Okay, so let's start our story with the 2x2 table that we should be pretty familiar with by now. And we have examined a few quantities regarding this table, which are the column-wise rates and the row-wise rates. So we have, for instance, the true positive rate, TPR, false positive rate, FPR, false emission rate, FOR, and then we have FDP. And here you might start to be a little bit suspicious. All the first three quantities are defined as rates, or the terms that we use for them have the word rate in them, whereas false discovery proportion is a proportion. However, they all defined in very symmetric ways, right? For instance, F of R is equal to the number of false negatives divided by the number of true negatives plus the number of false negatives. All right, and then FDP is defined as just the same notion, but for the right column instead of the left column, right? So the number of false positives divided by the number of true positives plus the number of false positives. Okay, so the reason why there's this difference in terminology is because the term FDR has been co-opted by the literature on multiple hypothesis testing. And FDR is instead defined to be the expectation of your FDP. All right, so in other words, it's the expectation of the ratio of false positives divided by true positives plus false positives. All right, so the definitions are different. However, the key question asked here is, what is the randomness here? Why do we not have to use expectations for true positive rate, false positive rate, and false omission rate? Well, the answer is that in the setting of binary classification, which we started the course with, these numbers, false positive, number of false positives, number of true positives, so on and so forth, these are fixed numbers. So they are no longer random at all. All right. So in other words, under the binary classification setting, when we define all of these quantities, the number of true positives, number of false positives, etc., are fixed numbers. Right? So we have a fixed finite population. And when we say that some of the quantities like FDP can be thought of as a condition of probability, right? And more precisely, it was defined to be the probability, or it was seen to be the probability of reality being equal to 1, sorry, reality being equal to 0, given that decision is equal to 1. The probability here, the randomness that goes into this condition probability, is a randomness over the finite, with respect to sampling over a finite population. Okay, so it's very different from the randomness that you see in the expectation that we use to define FDR. Okay, so FDR, with respect to the other setting that we consider, that the other setting that we have been considering in the last 1 or 2 lectures, and that is with respect to multiple hypothesis testing. So in this setting, the number of true positives, number of false positives, etc., are random quantities. Okay, so they depend on some underlying distribution of test statistics and also perhaps some randomness in your algorithm. Okay, so this means that even after you consider the FDP, right, so you consider this ratio over here, this is still a random variable. And so you can still take an expectation over the data generating process that gives you some number of false positives, true positives, and so on and so forth. Okay. And we see that with both Benjamin Hochberg and also with the new algorithm that you're going to see on Thursday, which is this LOT algorithm. So in that case, we have some model over the distribution of null p-values. And it's with respect to that distribution that we define the expectation of the FDP in order to get the FDR.